Hello everyone. Welcome to the revision series of chemistry by ANR. This is the series where I'm going to discuss all the organic named reactions. First is the Finkelstein reaction, where we can obtain alkyl iodide. We can obtain alkyl iodide from a chloro or bromo compound where X is equal to Cl or Br. So from RCl or RBr by reacting it in presence of NaI and dry acetone. Keep in mind that in presence of dry acetone, NaX is precipitated out. It is insoluble in dry acetone. And next is Schwartz reaction. These two reactions are under a series which is known as halogen exchange. That is, from one halo compound I can obtain another halo compound, be it iodide or fluoride. Iodide can be obtained from Rx, which is a chloro or bromo compound, and fluoro can be obtained from Rx, again chloro or bromo compound, in presence of NaX, Ag2F2, COF2 or SbF3. Next is Wood's reaction, which is a reaction to obtain symmetrical alkane. It's a reaction to obtain symmetrical alkane containing even number of carbon atoms. Why? Because when 2 moles of the alkyl halide reacts with 2 moles of sodium in presence of dry ether, because aqueous medium is avoided because sodium will react with water. Another thing is the formation of NaX, which is a precipitate in dry ether medium. Now, this alkyl halide contains even number of carbon atom because the number of carbon atom will be a multiple of 2. If there is n number of carbon atom in the starting alkyl halide, here it has to be 2n number of carbon atom, which is a multiple of 2 and is even number. Next is diazotization reaction, and this diazotization is the name of the process of formation of diazonium salt. Starting this benzene diazonium salt, which I have written, is a stable intermediate. If I obtain Rn2 plus Cl minus, this is unstable, which can be obtained from RnH2. It is unstable, it breaks down to give alcohol. But this benzene diazonium halide is a stable intermediate which is stabilized on account of resonance. That is, aniline reacts with aqueous NaNO2 and dilute HCl 0 to 5 degrees Celsius to form benzene diazonium halide, which is resonance stabilized. And most of the organic conversions, there we see the use of this important intermediate because many organic compounds can be obtained from this intermediate. Sandmeyer's reaction is another reaction where this benzene diazonium halide is reacted with Cu2X2 or in presence of HX, where X is Cl or Br, in order to obtain ARX plus N2. N2 gas is evolved. Now this again can be reacted with CuCN KCN to give cyanobenzene. This is the structure of cyanobenzene, and both these set of reactions is under Sandmeyer's reaction. Next is to obtain aryl halides, again chlorobenzene, bromobenzene, using the benzene diazonium halide intermediate in Gattermann reaction with copper and HX. Dow's process is the method of preparation. It's an industrial method of preparation, rather I will say, in order to obtain phenol from chlorobenzene. But remember, industrially and economically, phenol is better obtained from cumene, which we will discuss in the next video, where we will discuss conversions. So this Dow's process, you can obtain phenol from chlorobenzene using aqueous NaOH. If you give aqueous NaOH and you don't acidify it, then the intermediate is sodium phenoxide with ONa with the benzene ring. Now you need a high temperature, 623 Kelvin and 300 atmospheric pressure, and then you acidify it where the ONa gets converted to OH. So this is Dow's process where chlorobenzene can be converted to phenol. But remember one thing, that in chlorobenzene the CCl bond has partial double bond character. It's difficult to carry out this reaction, and so for that reason such a high temperature and pressure condition, drastic condition, is required. Fittig reaction is the method of preparing diphenyls with the 2 moles of aryl halide in presence of sodium and dry ether. Now, Wurtz-Fittig reaction is a method of preparing alkyl benzene. These are alkyl benzenes from 1 mole of alkyl halide and 1 mole of aryl halide in presence of 2 moles of sodium and dry ether medium. Haloform reaction is the reaction where you can obtain CHX3, which is haloform, and here I have given you iodoform. This is iodoform. CHI3 is iodoform. If I obtain CHCl3, it is chloroform. If I obtain CHBr3, it is bromoform. Why I have given iodoform? Because this test is used as a distinguishing test, because iodoform gives yellow PPT. That means this iodoform is insoluble and it's yellow in color. So which type of compounds respond to this test and which type of compounds can be distinguished? If you start with alcohol, remember alcohols containing CH3CHOH group that can get oxidized by the removal of H2 to CH3CO group. So this is known as ketomethyl group or methyl keto. So CH3CO is a ketomethyl group. So carbonyl compounds containing ketomethyl group or alcohols containing CH3CHOH group that can get converted or oxidized to a ketomethyl group reacts with I2 and NaOH that produces in situ NaOI. This NaOI is obtained in situ. In situ means in the reaction mixture. You cannot directly add NaOI, but you are generating NaOI by the reaction of I2 and NaOH. So you obtain CHI3 iodoform, which is a yellow PPT. Along with that, you remember that if you start with n number of carbon atoms, this CHI3 over there, 1 carbon is getting removed. So what remains over here is n-1 carbon atom, giving RCOONA, NaI and H2O. So 3 such examples I have given. This is not with NaOH, this is with sodium carbonate, Na2CO3, where ethanol is reacting with I2 and it is again giving you iodoform. And the next one, remember with with Na2CO3, you are also getting CO2. But with NaOH, you are just getting NaI and H2O along with the other 2 products. So these are the examples of iodoform reaction, the reactions which I have given, the 4 set of reactions. These are the 4 set of reactions. Okay. So now next, moving on, preparation of Freon 12 from CCl4 by Schwartz reaction. This is a specific preparation reaction since I have mentioned Schwartz. So this is one such example. CCl4 is carbon tetrachloride, reacts with SbF3, and when you heat it in presence of SbCl5, you get Freon 12, which is CCl2F2. Now next, Hunsdecker reaction or Hunsdecker reaction. This is, name of the reaction is not given in NCERT. I have just named it extra. Otherwise, RC double bonded OAG reacts with bromine in presence of CCl4 and reflux condition. Reflux is the process. Then this breaks to form RBr. you get RBr, you get AgBr, and here you can see CO2. So you are seeing RBr, AgBr and CO2. Next, hydroboration oxidation method is a method of addition of H2O in HOH manner following anti-Markovnikov manner of addition. So it is anti-Markovnikov manner of addition of HOH to an unsaturated system, where you are seeing that I have given unsymmetrical unsaturated system in order to show you in presence of BH3, that is hydroborane or diborane. Okay, so here you can see BH3 forms a dimer, B2H6 diborane, and then you see that RCH2 whole thrice B. If this I consider it to be R3B. Now this is what is happening. R3B, you are getting a boride which reacts with peroxide, alkaline medium, finally H2O, and you get the alcohol. Now keep in mind, it is like addition of HOH in anti-Markovnikov manner. OH is getting added to this containing more number of hydrogen, H is getting added to this carbon containing less number of hydrogen, and so you get this. So next, esterification reaction. This is also not a name reaction, it's the name of the process, esterification. Now this is the ester linkage which you are seeing, which can be obtained from acid, RCOOH, and hydride and acyl chloride. So in presence of R-OH, which is alcohol, all these are acid catalyzed reaction. Only pyridine is a base. Why? Because in this reaction you are producing HCl, so pyridine helps in removal of HCl and drives the reaction forward. So these are the three set of reactions by which you can obtain ester. Next is coal-base reaction. Now coal-base reaction and coal-base electrolysis, both are different reaction. In coal-base reaction you can obtain salicylic acid, that is 2-hydroxybenzoic acid, from phenol using NaOH forming sodium phenoxide. Why it is forming sodium phenoxide, why it is actually required to form sodium phenoxide is that CO2 is a weak electrophile. It's a weak electrophile. So for that reason, what happens is that the nucleophilicity of phenol is less in comparison to that of sodium phenoxide, which has a negative charge over oxygen. So sodium phenoxide has greater nucleophilicity, which reacts better with the weak electrophile CO2, followed by acidification to give you COOH, otherwise your COONA will be there, and this is salicylic acid or 2-hydroxybenzoic acid. Next is Reimer-Tiemann reaction. Here you are getting salicylaldehyde, 2-hydroxybenzaldehyde by reacting phenol with chloroform. This is chloroform in presence of aqueous NaOH, and you heat it at 340 Kelvin. This is the intermediate that you get, and again you give NaOH to get NaOH followed by acidification in order to get salicylaldehyde. So you can see it stepwise, or if the name reaction is being given to you, you can write the reagents together, that is number 2H3O plus you can give, and you can write the final product salicylaldehyde. Next is Williamson synthesis for the formation of ether. Ether linkage is carbon-oxygen-carbon linkage. Here you are using sodium phenoxide or sodium alkoxide, which acts as a nucleophile. So it can be alkoxide or phenoxide, but the substrate should be less bulky, so alkyl halide. Reaction is SN2 type, and so you get ether as the product. So when you get such questions where the ether is given and you are supposed to choose the set of the materials where from you can obtain this using Williamson, always keep in mind the more bulky one will always be the nucleophile. The less bulky one will be the alkyl halide. Because it is SN2 type reaction, substrate should be less bulky. Stephen reaction starts with nitriles RCN. It is reduction. This is a reduction process, so it reacts with H2. So H2 in presence of SnCl2 and HCl, which actually obtains, it produces the nascent hydrogen. So you remember in this manner that first you add H2 on both the sides and remove the triple bond to a double bond formation, and you get RCH double bonded NH, which is imine linkage, and then followed by hydrolysis, and you get OH2 getting added, and it is RCHO. If you use aryl cyanide or nitrile, that is from here you will get RCHO, which is benzaldehyde. So it is possible with alkyl or aryl nitriles. Next is Etard reaction, formation of benzaldehyde from toluene. So this is methyl benzene or toluene. It reacts with chromyl chloride. This is known as chromyl chloride. CrO2Cl2 is chromyl chloride in CS2 solvent. CS2 is the medium. This is your intermediate, followed by acidification, and you get benzaldehyde. So formation of benzaldehyde from toluene. Now if it is formation of benzaldehyde from benzene, you can convert it to toluene by Friedel-Crafts alkylation using CH3Cl anhydrous AlCl3, and then again you can follow Etard reaction in order to obtain benzaldehyde. Otherwise you can follow Gattermann-Koch reaction, where it is also known as formylation reaction. This is also known as formylation reaction, where you are using CO, carbon monoxide, and HCl in presence of anhydrous AlCl3 and CuCl, and you get benzaldehyde. So both the methods can be used. Clemmensen reduction, here it is done in carbonyls, aldehydes and ketones. It is again a reduction, so reaction with H2 in presence of zinc amalgam ZnHg in presence of concentrated HCl. So here in C double bonded O you get H2. So CH2, this is the hydrocarbon that is obtained by reduction of carbonyl plus H2O. Please see to it that the number of carbon atom is remaining fixed here. Wolff-Kishner reduction, again here carbonyl compounds, aldehydes and ketones, they undergo reduction. Here you can remember that here you are removing H2O. Remove H2O and join this carbon and nitrogen end by double bond, and you get this linkage. And then you add KOH in presence of ethylene glycol, and here there is addition of H2 by the removal of this N2. So N2 is the side product over here. H2O was the side product in Clemmensen. So here also you are getting CH2. This is also hydrocarbon. The number of carbon atoms are remaining the same here also, but the side products and the reaction conditions are different. Next, moving on to Volhard-Zielinski reaction, HVZ, which is alpha halogenation over carbonyl compounds. If this is the carbonyl linkage COOH, this carbon is your alpha carbon. So removing one H of alpha, you get halo group, and this is known as alpha halogenation in presence of X2 red phosphorus followed by H2O hydrolysis, and you get alpha position halo group coming. Rosenmann reduction is over acyl chloride. It can be RCOCl or ArCOCl, which is benzoyl chloride, and reducing it, so plus H2 in presence of PD, BaSO4 or sulfur quinoline. These are the catalyst poisons, and you are obtaining RCHO, aldehyde or ArCHO. Why do you need catalyst poison? Such that the aldehyde doesn't get reduced to primary alcohol, because you know that the reduction of aldehyde gives primary alcohol. So reduction is done in a controlled manner. So next, aldol condensation reaction is a condensation reaction using carbonyl compounds containing alpha carbon. They contain alpha carbon. So here what is happening, remember that this oxygen holds this H by protonation, and CH2 minus is the nucleophilic end that is being generated, which attacks the electrophilic carbon. So H is added to oxygen and the carbon, alpha carbon, is added to the carbonyl in order to obtain aldol. This is containing aldehyde and alcohol group together. So you can see beta hydroxyaldehyde. This is beta hydroxyaldehyde, and so this is known as aldol. If you obtain a ketol, that means there you are starting from a ketone containing alpha hydrogen. Now when you heat it, condensation means removal of a neutral molecule. So when you heat, there is elimination of H2O from the alpha and the beta. That is, H is removed from alpha, OH is removed from beta carbon, and you get alpha beta unsaturated aldehyde. You are getting alpha beta unsaturated aldehyde as the final product. So keep in mind whether there is aldol formation or there is condensation. If heat is not given, that means you will get aldol. If heat is there, that means removal of H2O, and you will get the beta alpha beta unsaturated carbonyl compound. Why carbonyl compound? If you start with ketone, you will get a keto linkage. If you start with aldehyde, you will get aldehyde linkage. Cannizzaro reaction is a reaction of carbonyl compounds containing no alpha H. That means it doesn't have any alpha H. Like HCHO, formaldehyde reacts with concentrated KOH or NaOH to give. It undergoes disproportionation reaction. So you get one oxidized product and one reduced product. The oxidized product is carboxylic acid. Presence of NaOH or KOH will give the corresponding salt, and you will get the reduced product, which is the alcohol. Next, ammonolysis reaction is the name of the process, ammonolysis. So you start with amine. This is your 1 degree aliphatic amine. Reaction with alkyl halide. This amine, the lone pair above, nitrogen, makes it act as a nucleophile, and RX acts as the substrate. So by the removal of HX, you get one H getting substituted by R. So you get R2NH. Again it can attack RX, and again there is elimination of HX. So another H getting substituted by R. So you get R3N. And the quaternary salt, this is your quaternary salt which you are getting, where there is no H remaining, but then also the lone pair above nitrogen can attack the RX on account of nucleophilic attack. So Hofmann bromamide degradation. Here degradation term means the final product is having one carbon atom less. If you start with n number of carbon atom, you get a product which contains n minus 1 number of carbon atom. So this degradation takes place in amides containing CONH2 linkage. It can be aliphatic or aromatic. So it can be RCONH2 aliphatic amide or ARCONH2 aromatic amide, reacting with bromine in presence of NaOH or KOH, which generates NaOBr or KOBr in situ. Again, in situ means in the reaction mixture. You are getting this by the reaction of bromine and NaOH or KOH. So you will get obviously RNH2 or ARNH2, which is a 1 degree aliphatic or aromatic amine containing one carbon atom less. So it is degradation. Why one carbon atom less? Because you were having the amide carbon, and here that carbon is getting removed and it forms Na2CO3. So remember this reaction along with the balancing. Iodoform reaction. Remember that reaction along with the balancing. Gabriel thalamide, like carbylamine reaction, iodoform reaction, Hofmann bromamide degradation. Now these all demands the balancing. Okay, Gabriel thalamide synthesis. You start with this thing, thalamide. This is imide of thalic acid. CONH linkage is there. The starting material is thalamide, and you react it with KOH, and here you are just increasing its nucleophilicity, just like in Kolbe. The nucleophilicity is increased. Here also nitrogen was having lone pair, now nitrogen is having a negative charge. So this has greater nucleophilicity than thalamide. So that you are converting it to the potassium salt. Now this is attacking over the substrate and you get R coming over here. So this is the alkyl substituted product and which undergoes hydrolysis, and also if you give aqueous NaOH, it breaks down in this manner. So the manner which I have said, nitrogen is holding H and the other end is having OH. So you get OH getting converted to ONA, and this is sodium salt of thalic acid, and you get RNH2, which is 1 degree aliphatic amine. Here I cannot say that you will get ARNH2 or aniline. Why? Because this reaction is SN2 type and your nucleophile, this is your nucleophile which is already bulky in nature, and so this substrate should be less hindered, sterically hindered. That can happen with RX and not with ARX. Moreover, ARX, aryl halides, are less susceptible to nucleophilic substitution reaction on account of the repulsion, on account of the partial double bond character of CX and many other reasons. So this is limited to 1 degree aliphatic amines only for that reason. Next, moving to carbylamine reaction, this also I said, remember, with the balancing. Here the starting material can be 1 degree aliphatic or aromatic amines reacting with chloroform in presence of alcoholic KOH. When you heat it, you get isocyanide which has obnoxious smell, and this can be used as a distinguishing test for that reason. For 1 degree aliphatic and aromatic amines, you get RNC, which is isocyanide having obnoxious smell, along with KCl and H2O. Remember the balancing. And don't forget to give the heat sign. Coupling reaction, again this is based on the process of the reaction. It's actually not a name reaction, it's based on the process. Just like esterification I said, the same manner. Just like diazotization I said, in the same manner. So once you do diazotization and you get benzene diazonium halide, it can react with phenol at an alkaline medium. This medium is alkaline, 0 to 5 degrees Celsius, using alkaline medium. If you do this, then you are going to get a dye which is orange dye, and this is the structure. Remember that you are removing HCl, joining this end to this paracarbon. So you get N double bonded N. And here don't forget to give this OH, which is para-hydroxyazobenzene. This is the azo linkage. So para-hydroxyazobenzene. So this is your azobenzene and here is the para-hydroxy and plus HCl. Now in the other one, this is the reaction with aniline, and the same thing, it is being done 0 to 5 degrees Celsius, but the medium is not alkaline, the medium is acidic medium with a pH of 4 to 5. So in acidic medium, so if you remember that aniline is dissolved in HCl, dilute HCl, and so you get it an acidic medium. Okay, and in case of phenol was dissolved in NaOH, it was alkaline medium. So here you are getting again a dye which is yellow in color, and it is para position, there is amino, and this is your azobenzene. So it is para amino azobenzene with HCl as the side product. So these are the name reactions for the sake of revision. I hope the video is useful to all of you. So bye all of you. See you in the next video.